Section 4.3 Linearly Independent Sets and Bases. First we're going to look at a definition. A set of vectors v1 through vp in a vector space V is said to be linearly independent if this vector equation here has only the trivial solution. So we basically have a linear combination of our vectors v1 through vp with c1 through cp as the coefficients, and the vectors are linearly independent if those coefficients must all be 0. So we have only the trivial solution. So then it should make sense that the set is linearly dependent if we have weights that are not all 0, so that our equation holds true, meaning we have a non-trivial solution. The following results from section 1.7 are still true for more general vector spaces, so I just want to remind you of them here. A set containing the 0 vector is linearly dependent. A set of two vectors is linearly dependent if and only if one is a multiple of the other. So bearing that in mind, let's look at an example. Are the following linearly dependent or linearly independent? So here we have a set of three vectors, or these are actually three 2x2 matrices, and we have shown in previous sections that the set of 2x2 matrices with real entries is a vector space. So we know that these are elements in our vector space, the M sub 2x2. And we see that we have the 0 vector in there as one of our entries. And so then we know that this is linearly dependent. In this set we have two vectors, so it makes sense that we want to look to see if they're multiples of each other to tell if we have a dependent or independent set. So if you look at it, you can see that our second entry here, the first three are multiples of these three entries in the first one. However, this 11 is not. So we see that this vector here is not a multiple of the first vector. So then this set is linearly independent. Theorem 4 says an index set v1 through vp of two or more vectors with v1 not equal to the 0 vector is linearly dependent if and only if some vector v sub j, where j is greater than 1, is a linear combination of the preceding vectors. So let's look at an example. We want to let the set p1, p2, and p3 be a set of vectors in p sub 2 where our vectors are defined as these three equations. And we want to ask the question, is this a linearly dependent set? So we're going to apply theorem 4, and we want to see, is one vector a linear combination of the preceding ones? So let's have a look. If we look at p3, and we see that it is 4t plus 2t squared, then recognizing that p1 is just t and p2 is t squared, then we could rewrite p3 as 4 times p1 plus 2 times p2. So we see then that p3 is a linear combination of the preceding vectors, and so it is a linearly dependent set. Now we want to look at something called a basis set. Here we want to let H be the plane illustrated below in this graph. Which of the following are valid descriptions of H? In part A, we have that H is the span of V1 and V2. So basically, from linear combinations of this vector here V1 and this vector here V2, can we get the entire plane? And the answer is yes, because I could, for instance, double V2 and have 0 times V1 and arrive at this section here. I could add v1 and v2 and get here. So every point on the plane is some linear combination of those two. So then we can see that that is a valid description of H. So is B, for similar reasons, because we could arrive at this point here by saying it's 1/2 v3 plus v1. So that will give us our entire plane as well. Now if I look at this one here, part C, I see that I only have this vector here, v2 and v3. These two vectors are going in the same direction. So there is no linear combination that will provide me with points over on this side. Any multiple of them and any linear combination of them will just give me vectors in this line here formed by those two. So far A and B work, C does not. Now D works as well because we do have this vector v1 included. So we will get, by some linear combination of those three, we can arrive at every point in the plane. A basis set is an efficient spanning set containing no unnecessary vectors. In this case, we would consider the linearly independent sets v1, v2, and v1 and v3 from our previous example to both be examples of basis sets, or bases, which is a plural for basis, for H. So let's look back at that example. So we would say that then A or B would be basis sets because it's an efficient set. However, D, which is a valid description of H, has an unnecessary vector. We don't need to have both v2 and v3. We do, however, need to have v1. In this definition, we're going to let H be a subspace of a vector space V. An index set of vectors beta, which is equal to b1 through bp in V, is a basis for H if, number 1, beta is a linearly independent set, and 2, H is equal to the span of our vectors b1 through bp, which are our vectors in our basis. So in this example, we've defined E1, E2, and E3, and we want to show that the set containing those three vectors is a basis for R3. Incidentally, that set is called a standard basis for R3. So the first thing I'm going to do is define a matrix A, and it's going to be a 3 by 3 containing our vectors E1, E2, and E3 as the column vectors of A. So that would be equal to this matrix here. We can see that our matrix A has 3 pivots. And since it's a 3 by 3, then we know by the invertible matrix theorem, the columns of A then are linearly independent. And similarly, the columns of A span R3 also by the invertible matrix theorem. So, using the invertible matrix theorem, we were able to show that these three vectors are linearly independent and they span R3. So then, using our definition that we just looked at previously, we can see that the set containing these three vectors is a basis for R3. In this example, we want to let S be equal to the set of vectors 1 all the way up to t to the n power. We want to show that S is a basis for P sub n, our space of polynomials. And incidentally, this will be the standard basis for P sub n. Remember that the space P sub n is our polynomials of degree n. So since S contains each of the individual terms that would make up our polynomials, then we know that S certainly spans P sub n. So the next thing we need to see is we need to see if S is a linearly independent set. So to show that S is linearly independent, we're going to assume that we have a linear combination of the vectors in S with C0 through C sub n as our coefficient. And we're going to set it equal to the 0 vector of P sub n, which is this vector here. So since we're setting those two equal to one another, we would see then that the coefficients would have to be equal, and that they're all equal to 0. So C sub 0 is 0, all the way up to C sub n is 0. So then we see that S is a basis for the set of polynomials sub n. In this example, we've defined three vectors, v1 through v3, and we're asking the question, is this set of vectors a basis for R3? So we're going to define a matrix A with those three vectors as the columns of A. And this would be our matrix here. We're going to row reduce this, so we're going to multiply here by -2 and add it to the second row to get this matrix here, and then here we'll multiply by -1 and add it to this row here, and we produce this matrix here. So we see then that we have 3 pivots, and this is a 3 by 3 square matrix, and since there are 3 pivots, we know by the invertible matrix theorem then the columns of A are linearly independent and they span R3. So therefore, the set of our 3 vectors, v1 through v3, is a basis for R3. So in all of these, we've been using the definition showing that our vectors are linearly independent and they span our vector space. In this next example, we want to explain why each of these following sets is not a basis for R3. And we're going to use some of what we learned in section 1.7 when we talked about linear independence as we look at these basis sets. Here we see I have 4 vectors, and each vector has 3 entries. So since there are more vectors than entries per vector, this set is linearly dependent, so it is not a basis. For this next set, I'm going to use these 2 vectors as the columns of a matrix A. This is now a 3 by 2, and remember that in order to be a basis that they need to span R3, and using our favorite theorem, Theorem 4 from section 1.4, we know that the columns will span Rm or R3 if there's a pivot in every row, that those are equivalent statements. But since there are 3 rows and only 2 columns, without doing any row reduction, we know there cannot be a pivot in every row of A. So then, using Theorem 4 from section 1.4, we know that the columns of A do not span R3, and so then this set is not a basis for R3. Now we want to look at a basis for the null space of A. In this example, we're going to find a basis for the null space of A where A is defined as this matrix here. So the first thing we want to do is we want to set up our augmented matrix where we have it equal to 0, since the null space is the solutions to AX equals 0. So here is our augmented matrix, and we want to row reduce it to get this matrix here. Now as we set up to find our general solution, we see that we have pivots here in the first column and the third column, and we have free variables in the second, fourth, and fifth columns. So we have then that x1 is equal to -2x2 minus 13x4 minus 33x5. x2 is free. x3 is equal to 6x4 plus 15x5. x4 is free, and x5 is free. So then we have x2 times this vector here plus x4 times this vector here plus x5 times this vector here. Now I'm going to call this vector u, I'm going to call this vector v, and I'm going to call this vector w. That's just for ease of writing. So therefore we see then that the set of these three vectors here, u, v, and w, is a spanning set for the null space of A. In section 4.2, the last section we looked at, we saw that this set is linearly independent, and since it's a spanning set, it spans the null space, then it is a basis for the null space. And remember, we're talking about the set of our vectors u, v, and w, which we defined here. These vectors are a basis then for the null space of A. We're going to look next at the spanning set theorem, but before we do, we're going to look at a couple things. A basis can be constructed from a spanning set of vectors by discarding vectors which are linear combinations of preceding vectors in the index set. So in this example, we've got v1, v2, and v3. So if x is a vector that's in the span of these three vectors, then we can say that x is written in this way, as c1 times v1 plus c2 times v2 plus c3 times v3. But if we have a look at v3, we can see that v3 is a linear combination of v1 and v2. It is 2 times v1 plus 3 times v2. So I can use this expression for v3 here. So I rewrite x as c1 v1 plus c2 v2 plus c3 now times 2v1 plus 3v2. So doing a little algebra, we see then that we get c1 plus 2c3 times v1 plus then c2 plus 3c3 times v2. So we've now changed and written our vector x as, instead of a linear combination of three vectors, as a linear combination of just two. So therefore we see that the span of my three vectors, v1, v2, and v3, is equal to the span of the two vectors v1 and v2. And that is due to the fact that v3 was a linear combination of the preceding vectors, so we could discard it essentially. So now let's look at Theorem 5, the spanning set theorem. Let S be the set of vectors v1 through vp, and it's a set in V. Then we let H be the span of those vectors. Part A says if one of the vectors in S, let's say v sub k, is a linear combination of the remaining vectors in S, then the set formed from S by removing that vector still spans H. And then part B says if H is not equal to just the zero vector, then some subset of S is a basis for H. So now we're going to look at bases for the column space of A. In this example, we want to find a basis for the column space of A where A is this 4 by 4 matrix. And it's made up of these column vectors A1 through A4. So the first thing we're going to do is we're going to row reduce our matrix, and we'll get this matrix here. And we're going to call this matrix B1, B2, B3, and B4. So each of the columns here are now going to be column vectors defined with B's. Now, in looking at this, we can see that the second column here is a multiple of the first. So B2 is simply 2 times B1. And we can also see that our fourth column is a linear combination of the first and the third. So B4 is equal to 4 times B1 plus 5 times B3. So we can link those and say that it's similar with our vectors A. So we see that since B2 was 2 times B1, then A2 is going to be 2 times A1. And we can look at it and see that A2 here is double our previous one, or A1. And similarly here, B4 was 4B1 plus 5B3, so A4 is going to be 4A1 plus 5A3. So let's look here. We have A4, and we'll just look at this last entry. Well, it might be easier here. Let's look at 22. We're going to say that it's 4 times 3, which is 12, plus 5 times 2, which is 10. So we have 12 plus 10 is 22. So it is true. Now notice that B1 and B3 are not multiples of each other. So then we see that A1 and A3 are not multiples of each other either. So what we're seeing then is that elementary row operations on a matrix do not affect the linear dependence relations among the columns of the matrix. So using our spanning set theorem, the span of my vectors A1, A2, A3, and A4 is equal to the span of simply A1 and A3. So we can discard B4 and B2 since they were linear combinations of one or both of these vectors. So then our set of A1 and A3 is a basis for the column space of A. Theorem 6. The pivot columns of a matrix A form a basis for the column space of A. So if we look back at the previous example, we see that the pivot columns were columns 1 and columns 3. So those columns of our original matrix, A1 and A3, is a basis for the column space of A. And doing all the work we did previously, we proved that that was true. So let's look at another example. Here we've defined V1, V2, and V3, and we want to find a basis for the span of those three vectors. So we're going to let our matrix A be equal to the matrix that has those vectors as columns. So A is equal to this matrix here. Then the span of those three vectors is equal to the column space of A. So we're going to row reduce our matrix A, and we get this matrix here. And we're doing this in order to apply theorem 6. And we see that I have a pivot in column 1 and in column 3. Therefore, by theorem 6, a basis for the span of V1, V2, and V3 is the set of our vectors V1 and V3. And I've actually written these out so that you can see that the basis is not the vectors in our row reduced matrix. It's the original vectors from the original matrix A. So here's a review. Number 1, to find a basis for the null space of A, we use elementary row operations to transform the augmented matrix with zeros as the last column to an equivalent reduced row echelon form B with zeros. And then we're going to use that reduced row echelon form to find the general solution to the system AX equals 0. The vectors found in this form are basis vectors for the null space of A. Number 2, a basis for the column space of A is formed from the pivot columns of A. And just like I was warning you in the previous example, it's important that you use the pivot columns of A, not the pivot columns of B, where B was the reduced echelon form that's row equivalent to A.